Okay, we toss a fair coin 13 times independently. We have two random variables we're defining from that experiment. One of them is how many times the coin lands heads in the first 10, and the other is how many times the coin lands heads in the last 10. Okay, 13 tosses in all, 10 and 10, first 10 and last 10 overlap, right? They overlap by 7. Yes? Okay, are x and y independent random variables? No, right? If you know that x is, for the sake of argument, 10, that the coin landed heads all 10 times, do you know something about y now? Yeah, you know that y has to be at least 7, right? No matter what happened. Okay, so knowing the value of x tells you something about the value of y. If you know that x was 0, you know that y can't be any bigger than 3. Yep, they're informative with respect to each other. Okay, here we've got an actual tabulated probability distribution. You're asked to find the expected value of x. How do you do that? What calculation do you do? The expected value is a weighted sum of the possible values, right? Where the weights are the probabilities. So we would, if we wanted to do this systematically, we could expand this table by another column and have a column that is x times the probability that x equals x. So the first entry in that would be 0.1111, right? The second entry would be 12 times 0.2963, et cetera. Then once we have those 5 numbers, how do we find the expected value? Just add them, right? Okay. What about the standard error? Okay, that's the expected value of another random variable. Which random variable? Well, sorry, it's the square root of the expected value of another random variable. Right? We'd find the expected value of x minus its expected value squared. Right? So once we found the expected value of x, we could have another column here that is x minus the expected value of x quantity squared. And then we'd have another column that is that times the probability. We'd add those numbers together, and that would give us the expected value of x minus its expected value squared. To get the SE out of that, we take the square root when we're done. Okay, straightforward stuff, mechanical. All right. We have a box with 6 tickets labeled with those numbers. And we want to find, we're going to draw with replacement from the box. And in problem 30, we draw 200 times with replacement. And the question is, what's the chance that the sum of those 200 draws is between minus 57.15 and plus 114.31? All right, first of all, what's the average of that list? It's 0, right? OK, so that's not too hard. Yep, it's 0 because for every number, there's the negative of that number. Yes? All right. OK, so to use the normal approximation, we need to be able to convert these numbers, minus 57.15 and plus 114.31, into standard units. Right? How do we convert to standard units? We subtract the expected value, divide by the standard error. The expected value of the sum of 200 draws from that box is 200 times the average of the box, which is 200 times 0, which I'm pretty sure is 0. Okay? The standard error of 200 draws with replacement from the box is going to be the square root of 200 times the SD of the box. So we've got to find the SD of the box. Okay? What's the SD of the box? Well, we're going to get minus 6 minus 0 squared plus minus 3 minus 0 squared plus et cetera, right? Divided by, there's 6 numbers in the box in all, and then we're going to take the square root of that. Yep. OK, so we've got 36 from each of those 2 terms on the end, the minus 6 and the plus 6. So we've got 36 plus 9 plus 4 plus 4 plus 9 plus 36. That looks like 40 twice is 80 plus 18 is 98. Yep, okay. So we've got 98 divided by 6. uh, 98 divided by 2 is 49, which is 7 squared, so that's not going to be divisible by 3. This is the square root of 49 over 3, which looks like 7 over the square root of 3. Okay, somebody want to do that? All right, so the SE of the sum is going to be equal to the square root of 200 times 7 over the square root of 3. Square root of 200 looks like the square root of 2 times 10 times 7 divided by the square root of 3. Somebody have a number? $57.15? Gee, look at that. Okay. All right, so this is one standard error below the expected value, right? 0 minus one standard error. The expected value is 0. And that looks a lot like 2 standard errors above the expected value. So what we're being asked to do, the normal approximation, once we've changed things to standard units, we're looking at the area under the normal curve from -1 to +2. Yep, that would be the normal approximation of that probability. Okay, what's that? Well, the area between plus or minus 1 is 68% roughly. So the area between -1 and 0 is half of 68%, right, which is 34%. So this part is 34%. And the area between plus or minus 2 is about 95%. Half of that is about 47.5%. Okay, 47.5%. So what do we have? 81.5% approximately. Now we have a really difficult problem, which is what's closer to 81.5%, 74% or 97%? Okay. Did that make sense? You just don't like it? Okay. All right. All right, suppose that we wanted to find the expected value of the sum of the squares on 200 random draws with replacement from the box. What do? How do we get there? The original box has the numbers -6, -3, -2, 2, 3, 6. If we're interested in the squares of the numbers on the tickets, we can just change this into drawing from a different box, where the labels on the tickets in the box are the squares of the labels on the tickets in this box, right? So what would those be? We would have two tickets labeled 36. We would have two tickets labeled 9, two tickets labeled 4, right? And so the expected value of the sum of 200 draws from the box would be 200 times the average of the box. Just take the average of this box.